Welcome to our webinar. Today's topic will be the Chip-DSC, a new innovative technology in the field of differential scanning calorimetry. On this slide, you can see today's agenda, which will be an overview of the DSC measurement principle, a comparison between the usual DSC and the new chip technology, the Chip-DSC sensor installation, an overview of the LINSEIS Chip-DSC series, the calibration, and how to perform a measurement. My name is Hans Marx. I'm the product specialist for DSC at LINSEIS. I did a PhD for chemistry at the Aachen University in 1994, followed by a postdoctoral research fellowship at the Bordeaux University, and then I became a technical support manager at LINSEIS in 2012. My spoken languages are German, English, and French, and I'm guiding you through this presentation. First of all, I want to explain the measurement principle of a DSC measurement. Simplified, you measure the temperature of a sample and a reference site and subtract the two signals from each other. On the left side here you see the sample site, on the right side you see the reference site. What you measure is the temperature on both sides and then you form the difference. If there is no reaction or phase transition occurring on the sample site, this difference will be zero because the temperature on both sides is the same. If there is a reaction or phase transition, like in the scheme on the right side, the temperature on the sample side will be lower if it's an endothermic process, or it will be higher in case of an exothermic process than the reference side, and therefore there will be created an effect that occurs as a peak. As an example for DSC measurement, we can consider the melting of an ice cube. While heating ice, the temperature of the ice cube will increase until the melting point at 0 degrees is reached. Any further energy is then used to melt the ice, but the temperature will remain constant at 0 degrees. When all the ice is molten, the temperature starts to rise again and creates the DSC peak. Now, let's have a closer look on the new chip technology in contrast to the usual DSC technique. As in the most cases the reference crucible is just an empty crucible, we were asking ourselves, why not integrating the reference into the sensor and also bringing the furnace closer to the sample? So the solution was to create a small chip design with an integrated furnace, sensor, and also reference. On the scheme below, you can see the scheme of the usual DSC on the left side with the reference and sample crucible and the resistance heaters at the side. The resistance heaters, also the sample thermometers, are now all integrated in a small chip where there is only one crucible remaining containing the sample on top. The advantages of the new chip design are, beside the smaller footprint that requires much less lab space, of course, a much faster heating and cooling due to the small thermal mass of the new sensor. It provides an excellent resolution and sensitivity, provides also a very easy handling, and of course it causes a much lower instrument price. On the scheme below, you can see the design of the chip sensor, and you can see that the active hot area has only the size of a thumbnail. The chip can also easily be exchanged by the end user within some seconds. The following video clip shows the exchange of a sensor. Sensor exchange and installation of a sensor can be done within 3 steps. In the first step, you have to open the screws of the glass case, like it can be seen here. There are 4 screws, 2 in front, 2 in the back position, that you can just open with one little turn to remove the glass part. After you have removed the glass part, you have to open 2 more screws on top of the sensor holder. After they are opened, you can remove the complete sensor holder by just plugging it out of the plug. After that, you can just pull out the blue sensor of its holder by lifting it a little bit with one finger and pulling it out. The new sensor can be inserted in the same way. You just have to put it into the sensor holder and then close it. The new technology is integrated in the new LINSEIS Chip-DSC series consisting of the following models. There's the basic version, the Chip-DSC 1, the more advanced model Chip-DSC 10 and the high-end version Chip-DSC 100. Now let's have a closer look on some instrument features. Let's start with the calibration. As every DSC instrument has to be calibrated, there's also a calibration process for the Chip-DSC. But in contrast to other DSCs, the calibration process can be done within only 15 minutes. There's an easy calibration mode where you can, for example, put 4 calibration materials into one crucible and just press run, and all the peaks are automatically analyzed and all the enthalpies are automatically integrated. You just have to confirm this by pressing the OK button and the calibration is already done. For more sophisticated applications, there's also an expert calibration mode. In this video clip, you can see the complete calibration process in a time-lapse sequence. You just have to type in the mass of the 4 calibration substances and then start the calibration process. On the green bar you can see the process during the calibration measurement, which will be completed within only 10 or 11 minutes in this case. After the process is finished, you just have to enter a file name for the calibration file that you can use for any measurement afterwards. Here you can see how to perform a measurement by measuring a sample of PET. The measurement of PET requires only a few steps. First of all, you have to prepare your sample, which can be a granulate or can be any kind of powder or solid sample. You put it into a crucible, determine its weight, then you open the instrument, put the crucible containing the sample on the sensor position, and then you can enter the data. There are only a few informations needed. First of all, you have to type in the name of the sample, then its mass that was determined before. Then you have to type in the heating rate, the target temperature, and then you can basically click on start and start the measurement. In the video, you can see the live measurement data in a time-lapse sequence. You see the temperature profile, the red line is the actual temperature, and the blue line is the DSC signal. After the measurement, you receive the measurement result that can look like in the scheme beside. In this case, it's PET that shows a glass transition around 80 centigrades, followed by a cold crystallization at around 150 centigrades, and then there's the melting peak at around 230 centigrades. Another particular feature are the extremely high heating rates up to 1000 Kelvin per minute that can be achieved. In the example on the scheme right, the melting point of indium was measured with different heating rates. Starting with 5 Kelvin per minute, it was done with 50 Kelvin per minute, 100 Kelvin per minute, 200 Kelvin per minute, 300, and finally 500 Kelvin per minute. And as you can see, the melting enthalpy remains constant. The biggest advantage of the new chip design is the fast ballistic cooling speed. On the video clip you can see in lifetime how fast the system can cool down without any need of active cooling. On the two schemes on the right side you can see different cooling curves that were recorded using the Chip-DSC. The blue curve shows the cooling from a 400 centigrade isothermal step to room temperature, which is achieved within 4 minutes. The green curve shows the derivative of the cooling speed that indicates that there is a maximum cooling speed of 500 Kelvin per minute at the beginning and at 100 degrees there's still around 90 Kelvin per minute cooling rate. This offers additional features and additional possibilities. For instance, TG or glass transition determination can be done much better because sometimes fast cooling is crucial for determination of glass transitions. And it also saves a lot of time. A complete polymer analysis can be done in just 10 minutes, including the cooling back to room temperature, without any need for any additional devices. This allows a throughput of up to 6 samples in only 1 hour, compared to only 1 sample per hour in a classical DSC, where you can see the cooling curve on the other scheme here. The Dutch Society of Thermal Analysis and Calorimetry introduced an experiment nowadays often called simply the Thorne test to compare the performances of different DSC devices. For this test, a substance that shows 2 peaks that are very close to each other is used. The scheme shows the Thorne test result for the resolution of the LINSEIS Chip-DSC in its basic setup at a heating rate of 20 Kelvin per minute. The resolution is given as the ratio of the minimum distance between the curve and the baseline between the peaks to the peak height. A low value, therefore, stands for higher resolution. The LINSEIS Chip-DSC achieves a value of 0.13, which means a very good high-resolution performance. A further interesting feature is the transparent cover. In classical DSC instruments, the sample can't be observed during the measurement. It's kind of black box. However, observation can give further useful information. For instance, forming of bubbles, fumes, the change of color, and many more. For example, some materials change their color at certain temperatures due to phase changes, which can be used in thermometers and other applications. This effect is called thermochromism. On the right-hand example, you can see the color change from red at room temperature to yellow at around 160 centigrades. The photos were taken during the measurement, and the corresponding DSC diagram can be seen above. The Chip-DSC can also be used for special applications like the measurement of high energetic materials. Highly energetic materials are often used in airbags as propellants or as blasting materials. For any type of DSC instrument, there is a risk of damaging the sensor and even the furnace. In the Chip-DSC, the chip, integrating sensor and furnace, can be easily replaced by the operator at low cost and in a very short time, as shown earlier in this presentation. This reduces the downtime of the instrument drastically. The example shows the DSC diagram of 2.8 mg of an airbag igniter. For some applications, low temperature measurements are necessary. For these kind of measurements, different cooling options are available depending on the Chip-DSC model. Even with the simplest version, the quench cooling option with manual cooling by liquid nitrogen, low melting points can be measured. On the left-hand example, you can see the Chip-DSC and the accessory for liquid nitrogen quench cooling. The sample curve shows the melting point of acetone at minus 95 centigrades, which can be used as a low temperature calibration material. Beside the hardware options, there are also software options available. One of them is the temperature modulation. A heating ramp with an overlaid modulation offers further experimental possibilities. For instance, the separation of reversible and irreversible phenomena or the measurement of the heat capacity Cp. On the right-hand example, you can see a sample curve that is compared to a reference. The two amplitudes are directly compared, and out of this comparison you get the measurement data you can see above. The curve above shows the calculated Cp data in comparison to the literature value. As you can see, the accuracy is better than 1.5%. Another software feature is the thermal library. It allows the comparison of measured DSC thermograms with those from a database. There's also the possibility to integrate your own materials and curves into this database. This can help to identify materials and check for their quality. In the given example, a PET sample, the black curve, was compared to the best fits of the database, the green curves, which are other PET qualities. Beside that, the next best fits would be PET blends with polyamide, shown as a red curve. The result is represented as overlaid curves and as a table with the respective quality of fit. Depending on the model, there are a lot of hardware options available. These options are a sample robot, various cooling options, for instance quench cooling by liquid nitrogen or controlled cooling by liquid nitrogen, or also controlled cooling by circulation cooler or Peltier cooling. Further options would be a camera for image acquisition during measurement, a pressurized DSC, or a UV lamp for triggering curing reactions. We like to thank you for your attention. If you have questions, you can contact us by email or by phone.